Be like an old person. Okay, Earth science time today. We're talking about, let's call this one Earth's formation. Earth's formation and history. More like herstory because Earth is a female. Earth is not a female. Earth is a planet. Earth is given female attributes by the poets. I'm going to rewrite this. I'm not going to rewrite this, but from now on I'm going to be writing in black so that it's more easier to see. Is this mic picking up? Are you picking up, Mike? Hey, are you picking up, Mike? Yeah, it is. Okay, now that we got all that stuff covered, marker color, amount of microphone gain, etc. Earth's formation. By what mechanism did Earth form? The reason I phrase it that specific way is because if I just say, how was Earth formed, you would be maybe tempted to say, the Lord God said, let there be light, etc. Which I'm not saying that didn't happen, but I'm saying by what mechanism, meaning what physical things happened such that then the Earth formed. Okay, we can start with the beginning of the universe, 14.5 billion years ago, there was a Big Bang. Let's fast forward quite a lot, through more than 3/4 of the history of the universe. Okay, yeah, space particles. Yeah, we have this is getting tangled up. My cord is getting tangled up. Space particles, yeah, we call a what? A blob, a gigantic blob of space particles, gas and dust, we call what?
Like an asteroid or a planet.
I draw it like this in honor of my buddy Kyla. A cloud, which in Latin is, as you know, nebula. Nebula means cloud in Latin, and so a big blob of gas and dust in the shape of a cloud floating around in outer space is called a nebula. And this, sometimes called a protoplanetary nebula or a stellar nursery or something like that, is a cloud that could or will eventually or has formed a star. By what force do these things then become a star? What is happening? Just no. By what force do these then become a star? Okay, I'm trying to do something. Please leave. God bless you. You've done a great job of that. I wish you were coming to a school instead of a nursery every day. What force causes this then to... Well, okay, let's start with this. What is the next step? What then happens to the nebula after some amount of time? What forms first?
Isn't it a star?
A star, yep. Some of us who aren't German pronounce it star, but yes, a star forms next. What has to happen to get from there to there? What this arrow is a process. What feature of the universe causes this star to... I'll make it easier. What force of the universe? It may be. That's an interesting hypothesis. But whether or not that is the reasoning behind it, she said gamma ray burst. You can look that up on your own. But whether or not that's the reason behind it, what force causes this nebula to collapse, as it were, into a star? Gravity. So the force both holding the solar system together and that formed the sun, part of the solar system in the first place, is gravity. So this, because of their mutual gravitational attraction, the particles that make up this cloud collapse through the force of gravity to form a star. Why is a star this shape? Everything has a shape because of a balance of forces. If you have a marker, this is a good drawing of a marker. If you have a dry erase marker, like I do, the reason it is this shape is the balance of its electromagnetic forces. The forces between the atoms make it this shape, and we can kind of use it as like a border to differentiate between this and the rest of the universe. That the border is the electromagnetic force of those atoms. It's not quite like that with the sun. The sun doesn't have the shape it has because of physical bonding of these atoms that make it up. It's really a balance of what's pulling it in all the time. Always every part of a star is pulling every other part of the star in towards its center. What is it? What's pulling it in all the time? Say it. No, you already know what it is. What's pulling all of the particles of the star together? Gravity. It's under constant attempted gravitational collapse. But it's held out by a balancing force of what? What is pushing an outside force from the inside out. Fusion, nuclear fusion, is always emitting energy. So the star, like our sun, is a balance of gravity collapsing it and fusion expanding it. What happens when the fusion stops then? It collapses even more. Our sun, in several billion years, will collapse into a white dwarf. But larger stars, the collapse kind of runs away and it becomes instead a black hole. And this has to do with what we call stellar evolution, the way a star changes over time. But this is the first thing that happened in our solar system. Started out like this. Now look where she is. The star is not the only thing, though. What else? After this happens, 99% of this is now this. But what is left? There's still some... Yeah, the other 1%, almost exactly 1% actually, is still floating out here as clouds of gas and dust. This is a very simplified drawing, but the rest of it, the rest of the 1% is still floating around as clouds of gas and dust, which they collapse, but there's not enough of them to start this process of nuclear fusion. So instead of collapsing into stars, these collapse into much smaller, first, still the sun. Now those are collapsing into, no. We call them at first planetesimals. Many of them collapse. There are lots and lots of them, probably millions of them, and we call them planetesimals. Remember that the suffix esimal, as in decimal, or infinitesimal, means very, very, very small. Infinitesimal means infinitely small. Planetesimal means a small planet. Decimal means a small 10. These planetesimals that form around the star themselves undergo gravitational collapse over a long period of time, and they become the planets that we know and love today, etc. None of this is to scale, FYI. None of it is to scale. Obviously, planets are not this size relative to the sun. They're much, 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 much smaller. And how long ago did this happen? And according to whom? Someone just guessed? How long ago did this happen? Say it. You can see it on there.
The beginning of the Hadean was like 3,850 megaohms ago, so it'll be like 13 billion years or something.
There's more below that, though, isn't there? There's more below 3850.
Yeah.
The Hadean. And that lasted about 700 million years, so that is, and it's like cut off there. You know how sometimes a chart will have a break? The Hadean's not really shown here. 4.5 billion years. So this all happened 4.5 giga-annum. We finally had planets. This process itself may have taken, I don't know, if I'm guessing, which I don't have any research or evidence at all for this, but if I'm guessing, maybe from the time it was just a nebula to here, maybe a billion years. So maybe it started much earlier, but by the time there were planets, it was about 4.5 billion years, 4.5 giga-annum. What evidence is there for that? We saw in the video several things. Was that you guys that we watched the video with? Me and the 8th graders watched a video that you would have really liked, but you did not watch. The evidence for this is space rocks. So we can tell Earth is this old because of space rocks. Why would we have to use space rocks? Why can't we just go out to find some old rocks on Earth?
Because the solar system is older than Earth, I guess.
Okay, that's one fairly good reason. Although we would still, if this is the age of the planets, we would still expect to find some on Earth since Earth is a planet. Why don't we, though? What's special about Earth?
That it's changing like
Yeah. Always eroding, always basically falling apart. Always the rocks are being remade, melted. The rock cycle stops us from having any rocks. I think the oldest rocks that we've ever found on planet Earth are somewhere between 3.8 and 4.2 giga-annum. So how do we know that Earth is 4.5 giga-annum then? Like I said, space rocks. Space rocks are not subject to erosion. They cooled right probably in one of these two stages, right when the planets were forming. They must have. All this formed together. And so if we know the age of a space rock, which, by the way, which of the ways that we discussed the day before yesterday, that's not true, Thursday or whatever it was, the time before last that we had a discussion, which of the ways that we discussed would we use to tell the actual age of a space rock? Could we use relative age dating for that?
No,
No, because all relative age dating could tell us possibly is that this space rock must have existed before it crashed into Earth. That would be the closest thing we could with relative age dating. But we would use absolute age dating, radiometric dating. And consistently, when we radiometrically date chunks of comets and asteroids that have landed on planet Earth, they are dated at this age. So since that's consistent, and since the oldest rocks on Earth are younger than that, we can pretty safely estimate that Earth must have been forming about 4.5 billion years ago during the, back to this guy. How do we read this? This is the geologic time scale. Where do we start? Where's the first thing on here? Yeah, we start in the Precambrian column, which that's not, we talked about this last time and we didn't have the chart, but let me hold this up in that way if you're watching that you can pause it and look at it. Going to be pretty hard to read. Good luck. But the, yeah, we have, you see that the Precambrian column on there, which is the rightmost and the oldest, is broken up into eons, eras, and periods, whereas the other ones are broken up into period, epoch, and age. So it tells us the eons. So what are the eons from oldest to current? And you can find this in your notes because we did talk about this before, or you can find it on here. What's the oldest eon? Hadean, followed by the Archean, followed by the Proterozoic. Can you see those things all on your chart? So we're going from the bottom right up the right column. And Precambrian is not an eon. Precambrian is telling us all the time before the Cambrian period, which we use kind of as the division because not life. Life probably existed about 3.5 billion years ago. We'll talk about that in a second. But sometime in the early Archean is the first evidence of single-celled life. But in the Cambrian is when life kind of as we know it, multi-celled life exploded in what we call the Cambrian explosion. When I say exploded, I don't mean they all blew up. I mean, like when you put toothpaste in the microwave, I mean that it diversified rapidly. There was a explosion of biodiversity in the Cambrian. So then we have, within the Proterozoic, so all of these, and this might help you, all of these, do one of these curly brackets, and put all of these are in the Phanerozoic. All three of these leftmost columns make up the Phanerozoic eon. So we had the Hadean eon, the Archean, and the Proterozoic, and then within the Phanerozoic eon, which you don't remember how to spell, so look in your notes, and also there's no way you can read what I wrote on here with a dry erase marker. PH, it's Phanerozoic with the PH, yep. Phanerozoic, P-H-A-N-E-R. O-Z-O-I-C. O-Z-O-I-C. Eon. So then next, what are these individual things within the Phanerozoic eon? These Paleozoic, Mesozoic, and Cenozoic are?
Are they like time periods?
No, they're not periods. They are. Periods are listed within them, so they must be.
Are they ages?
No, ages are listed within them. They are. The whole thing is an eon. The whole Phanerozoic eon is those three columns. Each one of them is what's in between eon and period from your notes. Or from your chart, I guess it'll say. Era. They are eras. The Paleozoic era, the Mesozoic era, and the Cenozoic era, and that's the order. So we start at the bottom right, go up the right column, then we're in the middle right column, start on the bottom. What are the periods of Paleozoic time? Well, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, and Permian. And we can go within the Cambrian, what are the epochs of Cambrian time? But we're not going to get that deep into it. And then within the Mesozoic, as I said, you need to have memorized the Triassic, Jurassic, Cretaceous. And then the Cenozoic, we have the Paleogene and Neogene. But some of these cowgirls who've been doing geology for a long time still call the group, the Paleogene and Neogene together the Tertiary. Paleogene, Neogene is a better division because it's more even than Tertiary, and then look where the Quaternary is. It's just this tiny little smidgen of the last, what does that say, 1.8 million years. So we have an awful lot of time differential between the Tertiary and the Quaternary that the Paleogene, Neogene, Quaternary makes a better division of. So the oldest time then is what do we call the oldest part of planet Earth? Or the oldest time of planet Earth? When this kind of thing was occurring, when it was just forming. When it was, as it were, without form and void. What do we call that? This time is the Hadean, which refers to what? You probably know. Hades, which is hell. Yeah. Hades, the Greek god of the underwood. It's just old Toby sitting down there. Oh, at Toby Underwood. God bless her. Underworld. That's pretty funny. I'm going to tell her that. Hades, god of the underworld, which is kind of commandeered by Christian mythology to then be a euphemism for Christian hell, such as that is perceived to exist. But that word means hell-like. Why would we call it that? Just for fun, just to make it so that teachers have a chance to say a bad word for once?
No, because Earth was literally just like on fire.
It was on fire. It was a blob of not fire, but lava. Lava, magma. The whole thing was magma. Why? Why was it so hot? Space is cold. It formed in space. Space is cold, in quotes. Why was it so dang hot?
Well, because it like just formed. Because it
Okay. Formed through what process, as we said before? Collision and what force holding it together? Gravity. So the things are still gravitationally pulling in, just like the sun gravitationally collapsing. This gravitational collapse generates a lot of heat. So there's heat due to gravitational collapse, and also heat due to nuclear radiation. Heat due to gravitational collapse and nuclear radiation. That's still how nuclear power plants work. Nuclear radioactive isotopes generate a lot of heat. That's still how how nuclear power plants work, and that's one of the reasons why not only was Earth so hot then, but why it's still warm inside of Earth now is from nuclear. In fact, it's the main reason that Earth is still warm now. And because of that, all of Earth was more or less liquid. And what's true of a liquid? If all of these things are liquid, how do things behave in a liquid, depending on their density? Things with higher density do what? Let's try one more time. Things with higher density sink. And so within Earth, we get a sinking of higher density stuff, such as what? What elements would we expect to find then within the very center of Earth? Of kinds of elements from the periodic table. Would we expect to find mostly non-metals like oxygen and sulfur, or would we expect to find mostly metals? Metals, because they are generally denser. And so that's why Earth's core now is iron and nickel. How do I know Earth's core is iron and nickel? I know because I read it. How does someone know that Earth's core is iron and nickel? Because of Earth's what? That only exists due to iron and nickel and the spinning of them. Earth's looks like this. Magnetic field. The magnetic field that exists around Earth means that something about Earth must be iron and nickel because they are paramagnetic. No, they are ferromagnetic. And so one piece of evidence that Earth's core is iron and nickel is that, and the explanation for it is that when Earth was liquid, the heavier things sank to the middle, meaning that the crust then is made mostly of what? Crust is made mostly of what kind of elements? Yeah, silicates. The silicates in the crust are the lightest of the minerals. Silicates in the crust. So the Earth, and we call this process differentiation. It differentiated into layers. It became different layers. Next step, so is getting, as this cools and becomes after a while, Earth becomes, it does what? First it's liquid rock, because it's so hot. And then as it cools, it becomes solid rock after a while. Let's date that at about the Archean. Let's put it at about 3.8 gigaonum. It becomes solid rock. And then it's Earth. But it's not quite Earth because it's missing something. What is it missing, as you were just about to say? Yeah. About 3.8 gigaonum, also the late heavy, or the early heavy bombardment. We'll just call it the heavy bombardments. What's bombardment mean? What does it mean if I bombard you with insults? What does it mean if, well, it comes from the word, like, if a ship bombards another ship, what does that mean? It's shooting cannons at it. So if I'm bombarding you with compliments, we'll say, that would be nicer. If I'm bombarding you with compliments, it means I'm spitting compliment after compliment after compliment to you. Same thing with bombarding you with insults or questions. Freshmen bombard me with questions means that they're constantly asking questions. What might this mean in the context? What is bombarding Earth? A spaceship? A guy with compliments? Freshmen with questions? No, what's the bombardment here?
Isn't it space rock?
Yeah. I like that. I was going to put asteroids, but that's not quite true. Space rock is better. And then within each little space rock, not each, but within many space rocks, is a tiny, 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 tiny bit of water. Hydrogen monoxide, some of us might say, but water. Each little space rock has a tiny bit of water. But there's a lot of space rocks, and over a lot of time, the water collects. And so at about 3.5 gigaonum, we now have watery Earth. And I'm going to put an about there. Now it's like Earth. We got land, we've got ocean. Now it's like Earth. No. What is it missing? Life. Specifically, so first life to develop is obviously what? What are the attributes of first life? Prokaryotes. Yep. They would be prokaryotic, but they would be single-celled. Right? They just have one little cell, and then you should know the words prokaryote and eukaryote. I'll remind you, but they are your responsibility. A prokaryote is a cell without a nucleus, and a eukaryote is a cell with a nucleus. The Greek word karyos means seed or kernel. So those cells that do not have a nucleus are called prokaryotes, like before the nucleus, the seed. And those with a nucleus are called eukaryotes. Eu meaning true or good. They truly do have a good seed in them. A good little nucleus is the way you can remember it. And now it's like Earth. No. Well, now what's it missing? Do you know? This one, I think this is the most exciting one. This was about 3.5 gigaonum too. No? Yeah, it is missing plants because there aren't any. But the next thing that comes up is oxygen. The atmosphere before this was probably mostly carbon dioxide, nitrogen compounds, nitrogen dioxide, and nitrogen trioxide. There may have been some things like sulfur dioxide and trioxide, but there was not oxygen. How did oxygen come to be here? Absorbed from outer space?
There was those little thingies.
Those little guys,
The
yeah.
ocean.
Those little guys, they're actually in kind of the shallow seas. They are little guys, but they form colonies of big guys. So these colonies of what we call stromatolites still exist. Stromatolites or stromatolites? So stromatolites? You might have to check the spelling on that. But they're colonies of, so they're about the size of, if I laid down and planked on this, that's about the size of the stromatolite. I don't know. That's a stupid example, but it's not a organism. It's a colony of cyanobacteria. Hey, why did he change to green for cyanobacteria? Because they can No, almost the opposite of that, actually. Why are they green? They can
Produce that one.
What is it called?
That.
What is it called? What's the process called?
Oh, photosynthesis.
Photosynthesis. These guys photosynthesize for the first time ever. And they are very good at it. Well, they're not good at photosynthesis, or not as good as today's organisms probably are, but they are better at getting energy than anything else. Until now, all the energy that life had to be absorbed from sulfur or nitrogen compounds called chemosynthesis, which is a pretty inefficient, some organisms still do that today, pretty inefficient way to gain energy. Or they had to eat other organisms that were doing that, which is similarly inefficient. But the first things that could photosynthesize that we know of were these cyanobacteria, and they could take, you remember photosynthesis, they could take carbon dioxide present in the atmosphere, they could take water present in the water, and in the presence of sunlight, they could make glucose sugar and as a byproduct. This is not the design, but as a byproduct, this is produced. And because they were so successful, it was really produced, and within only about 3.5 gig on them, and within only a few 100 million years, or maybe even with just tens of millions of years, the atmosphere was now 20 to 30% oxygen, where it was 0% oxygen before, because they were so good at this. And that was terrible news for these other guys, because they got outcompeted, and the oxygen is toxic to them. And so most of these other things, these old things, went extinct, the fossil record shows. The stromatolites changed Earth's atmosphere forever. And why is that important to us? Is because we need to have the oxygen. We really like the oxygen. What evidence do you think there is of this? Even now, even though there's no leaves on the trees, you can watch this happening right now. And you can measure, you've done a lab in biology, where you can show that the oxygen comes out. Like you grind up the spinach and put a light over it, and even though those things not all the cells are dead, even though you ground up the spinach, and you can observe the oxygen bubbles. We can watch this happening with our own eyes, and all we have to do is scale it up and move it back in time. Remember uniformitarianism. We're out of time to talk about the next thing we would talk about is the Cambrian. I think what we'll do, instead of me making a discussion for these three tomorrow, is we'll watch a video that will incorporate this and the events of these three, which will mostly focus on the kinds of life, which I think you already know about. Generally, going from, this was all single-celled here, right? To the time of invertebrates, to the time of fishes, to the time of, we sometimes call this the time of plants, but there was a time of amphibians and reptiles. This whole thing is the time of dinosaurs, and this whole thing is the time of mammals, and then this tiny little bit at the top is the time of humans. But generally, there are two things that this next portion would be if I were teaching it, which is how the tectonic plates would have made Earth's surface look, very briefly, and then what was going on with life would be the main thing. And so as long as you know those things generally, as I said, invertebrates in the Cambrian, invertebrates and kind of fishes in the Cambrian, fishes in the Devonian, in the Ordovician and Silurian, reptiles in the Devonian, trees-ish, not quite trees, but plants in the Carboniferous, reptiles in the Permian, dinosaurs in the Mesozoic, and mammals in the Cenozoic. That's what we would do, but we'll watch a video instead because it'll be more exciting. They'll have like dinosaurs running around and stuff. The last thing is, I kind of forgot to mention this, but there's things on your test about supercontinents, including Rodinia and Snowball Earth, but that will be in the video that we watch tomorrow, but those things are from this time, not the rest of what we would talk about tomorrow. Do you have questions about any of this? Earth's formation and history. Tristan, you have a question? Camden? No? You all good? Okay.